So again, just a quick reminder that this is not the first time you guys have seen parallel series circuits. There are, in the basic industry, basic electricity, guys, there are two types of circuits, as you know, the series or the parallel. You're looking at a series circuit. Parallel circuit, you can look at parallel circuit in a second. What I want to bring to the equation is I'm just going to quick review the rules of the parallel circuit and see the application of these parallel circuit, and then we're going to move on. Series circuit, guys, is just very quick, one path, right? As you can see, one way street, one path, current, same I. Number 3, V total equal V1 plus V2 plus V3. Voltage adds up across the resistors, right? So number 4, P total, the total power adds up, P1 plus P2 plus P3. These are the rules. So the current stays the same. It's one-way street. You go just in a loop, right? And the current stays the same. The voltage adds up to the source voltage, as well as the power adds up to the power voltage. The last rule that I would like to mention is 5. R total equal R1 plus R2 plus R3. If you guys don't know that, just a quick refresher. That's basically the rules of the series circuit. Disadvantage of this circuit, obviously, if you break any break in the circuit will screw up the whole circuit, right? The worst thing that could happen to you is you wire your microwave, air conditioning, and everything in this way. So if you lose one, you lose all of them. Just FYI, the industry have standardized. There are two ways. I don't know, Chris. There are two ways of manufacturing equipment. Two ways of manufacturing equipment. One way is to or making power system, making the whole power system. One way, guys, is to make the current constant and change the voltage. The other way is to make the voltage constant and change the current. And the international community, not just in the US, everywhere else, they took the second option. The second option is make the voltage constant and fluctuate the current. And that's what we designed in this panel. This panel, for the most part, the voltage in this panel is 28120. Doesn't go from 28120 to 10 volts. The voltage stays the same, and what fluctuates with the voltage is what? The current. So based on this rule doesn't, the series circuit cannot give you, if you guys look at the voltage, does the voltage fluctuate here with the load? As you add more or less load, the voltage across the load fluctuates. So at one time, you might have 10 volts here. Add another load, this will go 20 volt. Bad news. We don't design equipment for this, for the most part. You can see the most important thing is fluctuation. The voltage fluctuates. That's not how we make equipment. We make equipment constant voltage, current fluctuates.
When they see the voltage is constantly fluctuating.
Well, within the range. When I say fluctuates, change, I say double, triple, go half, 1/3. Yeah. Within 5 to 10% fluctuation of voltage, that's acceptable range. But I can't double or triple or quadruple the voltage like it does in the series circuit. So can you guys see the disadvantage of this circuit is this right here. We don't make equipment, we do not make equipment that actually fluctuates with the voltage, except for the most part, right? You don't make an air conditioning as when I put my microwave on, the voltage in air conditioning goes from 240 into 40 volt, and the air conditioning is still working. We could make equipments like this, but they don't make it. That's a disadvantage of this circuit. Any question, guys? So that's basically the most important disadvantage of it. I'm going to keep going on that one. Okay, series circuit. All right, go back. Okay, here we go. So the disadvantage, guys, again, the other disadvantage, obviously, if one load goes, all the loads will go. Talk about reliability in a power system. Are you kidding me? One load goes, all the other goes with it. Okay, here's so that's, we know what the rules are. Now let's look at an application of a series circuit, guys. One good closed loop 2-wire series circuit. You wired this in our lab. Did you guys wire this in our lab? You should have wired something similar to this in our lab. If you guys look at that circuit, you're looking at a series circuit here, from right here all the way. What I want to highlight here, everything is connected in series or in parallel. So one advantage of series circuit is control. In control, it makes a lot of sense to put things in series. For example, I want you guys to look at the overload and the magnet starter and this contactor device. They're all in series, tied to a voltage of 480 right here. That's a good application of a series circuit. Where control is really good. Take this. If I want this light to be controlled by Chris and by Nick, and unless Chris and Nick agree both at that turn the light on, the light will not go on. So what do? You put two switches in series, you give one to Chris and one to Nick, put them in series, unless both of them say on. If one of them say on off, it's not going to make anything, unless the other person agrees. That's what a series circuit is. Now, who cares? That's a major concept in the control industry. Major concept. I need two things to agree before a third thing happens, right? That's a series circuit, rule of a series circuit. Any question, guys, about this? Any question? So that's a good application for a series circuit. So what I want you guys to, practical application, signal circuits. Another good application of a series circuit. There you go, signal circuits. If you guys are looking at a signal circuit or a security system, and I have all these contacts, I want you guys to look at all these contacts. 1, 2, 3, 4, 5. All these contacts are normally closed contacts, right? Normally closed contacts in series. So I put them around the windows. If somebody's breaking any window into the house, they're all in series, right? So it will de-energize this coil, and by de-energizing this coil, this will pull in, and the alarm will go off. That's another application. Again, control circuit. Control and signaling is a great application of circuit. We teach here at Dunwoody, guys. I taught a class, and we still teach it, called schematics. Unreal. How many coils and contacts you can put in series to make things happen. So did you guys do logic in our math? Or and and. Series is an or. Two things have to happen before you do something, before a result will come. And is a parallel circuit. Two things, one thing have to happen. If one thing happened in an and, which is on, 1, 1, something to happen, then the outcome, if one of them is 1, the outcome will be 1, right? One of them can't control the outcome. So just keep this in mind as a series circuit in signals, as well as in a signal circuit. Internal equipment wiring. You guys have done this with Ryman. One of the most important things for series circuit, guys, take this. I need to make, the smarter than Chad decided, instead of making a 3 horsepower, guys, that run at 240, and another 3 horsepower that run at 480, you know what they do? They make the same one piece of equipment, and they put 2 coils in them. Here's a 120 and here's a 120, right? If you attach these 2 coils in series like this, you got your 240 and you run the motor at 240. If you parallel them, you will run them at 120. That's a major application for motors, transformers, and generators. Motors, transformers, and generators. So what's the advantage? A series circuit will give you a higher voltage when you series coils. Any questions about this? And you were looking at it? If I tie these 2, are they in series? These 2 are in series. Yup. See how it's tied here? No problem, Chad. You get yourself a higher voltage. You always get a higher voltage. And if you put these 2 coils, 1 coil and 1 coil, are they in series, tied together? Yup. You get yourself a higher voltage. You get yourself a higher voltage in a 3-phase or a single-phase system. And I know you guys touched on that one, but very, very important concept when you go, especially if you, I don't know where you guys would do that. You're not electricians, so to speak. But if you were to design something, you want to take 2, for example, take this problem. I want you to design a 600 volt motor. No problem. And also can run a 300 volt. No problem, Chad. I can design a coil that runs at 300 volt. You can, by adding more coils, and design 300 volt and another 300 volt, tie them together, got you a 600 volt, right? and then that will get you a 600-volt motor if you were to design a motor like this. So any question, guys, about seriesing the coils to get you a higher voltage? Very big concept in the design. Motors, transformers, and generators unparalleled. So that's a major concept when you use them. I'm not going to do the series calculation, guys. You know, you've done a lot of these series calculation, adding, and I'm going to let you, I trust you that you know the rules, the 5 rules that we did. One rule dear to my heart, guys, is the power rule. And the rule that screw up the whole parallel circuit, series circuit is what? The fluctuation of voltage. Voltage cannot fluctuate in equipment. Air conditioning need 240. I can go to 230, but I can't go to 100 volt. That's called too much fluctuation in the voltage. That's why we can't use it in the power. In the control, no problem. Control industry, no problem with devices. So I'm gonna move fast on these. The resistance, guys, are the total resistance. You're familiar with that. You've done that. So I'm gonna move quick on this. The voltage, we talked about the voltage. Right? Am I going too fast for any one of you guys? These are I hope you can you did the voltage drop across each resistor. If I ask you what's the voltage drop across each resistor, you take the current that passes through every resistor and multiply by the resistor itself. You get you from Ohm's law the voltage across each resistor, right? So that's and then you add all the voltages. It should equal to the source of the power source. Otherwise, you have just created a new science. You just created new science. I like this one. This is what I like about this chart, guys, and you have in your book. What I like about, and that's why we specify this book for you guys, because really nice graphics. What I like about this, I want you guys to look at this. Very important. The impedance of the load. Can you guys see that? Compared to the impedance of everything else. Can you guys see that? This is one of the single most important thing in any circuit. The impedance of the load is 95% or higher than the impedance of the source and all the conductors. That's why we can pump the power. We can pump the power from Becker all the way to New York City through the grid because of fluctuation, because of the impedance. You reduce the impedance in the transmission line, and you push the power directly through the loops. The worst thing that could happen, guys, to you is most of the power that you do, it's consumed by the generator that generates it. Well, how efficient that would be. You want the generator and the conductor that transmit, the generator that generate the power and the conductor that conduct the power, you want them to consume very small amount of power, because the most of the power you want to shift it to the loads. Those are the customers that pay you. So can you guys highlight this one? This is the single most important thing in any circuit, not just in a series circuit. In any circuit, not just in any circuit. Again, I want you to add, look at this, guys, all the power generation transmission compared to the power generation transmission here. The voltage, you want the voltage across the source and in the conductor to be very limited compared to the voltage that's going to reach the source. And what we're doing, here's my load, guys, and here's my resistor, this is my load, and this is my source. The source right here, and that's what we're talking about here. This is my load, and this is conductor, of course. Conductor. This is generator. So you want all the voltage and all the voltage to be right across, all the voltage and all the impedance to be right across the load. Any question about this? Please understand this one fully in any circuits, not just in parallel circuit. The impedance and the voltage and the power, everything has to be, 95% of it has to be hogged by the load. If the transmission line takes half of your power, you're not going to stay in business for a long time. If I need to transmit 100 watts from here to Phil, right? And halfway through, I lost 50 of them. So thank you, Phil. Now I'm generating 100 watts. And you need 100 watts, but guess what? Halfway through, I lost in the process. So you got 50. So I'm not going to stay in business that much if that's how I generate and transmit power. I can't emphasize that percentages wise. I like this one from a percentage point of view. That will tell you how efficient transmission line or distribution line building. done with it. The voltage comes to us at 480. When I reach this panel right here, I better get as close to 480 as practical within 5 plus or minus 5%. You don't want to reach here and you get from 480, you get down to 240 just by impedance of the conductor. So, okay, enough about that. Kirchhoff's law, you guys have done the Kirchhoff's law. The current that enters, the voltage across, the current that enters is the same, and the voltage, the source voltage equal the sum of the voltage in all, the voltage drop across all the resistance. You have done a few of these, so I'm going to move fast on that one. This calculation. Power is my favorite. Okay, let's go to the power a little bit. Okay, determine the power. You guys have done a few of these, so I'm going to go directly into the graphic. Come on, Chad. Okay, series determine the resistance, and okay, I just want to emphasize a little bit when we talk about the power total for step 3, and you guys, power source. Power calculation, here's what I want. Come on, Chad. Power calculation. Okay, so the power, I want you guys to understand that the power is supposed to go from here into here with minimum losses. The power is supposed to go from the source to the load with minimum losses. So if you have the power that's consumed across the coil, the total power here, the total power, the whole system, appliances power. I want you guys to highlight this one. See how the majority of the power went where? To the source. That's what they pay me for. This is losses, bad news. Power, losses, bad news. The conductor 2 losses, bad news. The power should, if you generate 100% power here, you should be consumed up to probably 90% loss power right in here. Otherwise, you can't stay in business that much. How do you do that? By minimizing the losses in the conductor, bigger conductor, by making your equipment that generate more efficient, less losses in the equipment. Does that make sense? And I know you guys everybody knows how to calculate the power. You take the voltage multiplied by the current, or square the current multiplied by the resistor, or square the voltage divided by the resistor. I'm not going to go through the mathematics. You guys should be very familiar with it. I'm going to talk about the concept. The concept of Becker power plant, nuclear plant here, making 100% power coming to the city of Minneapolis. You better get close to 95% or higher. There will be losses, guys, in these interstate highways, right? These electrical interstate highways that are going, that's called the grid. There will be losses, but you don't want to have a whole lot of losses, though. Otherwise, you wouldn't stay in business for long. Okay, got that one. Power circuit.
When you're talking about the loss from the power supply, is that transformer efficiency? Or
yes, efficiency of the generator, thank you, and the transformer. The generators and transformers, guys, mainly generators, because that's where the power started. Transformers just moving the voltage from one level to another. They have impedance on them, and they have losses. Mechanical losses and electrical losses. They have mechanical and electrical losses on them. Okay. I don't know how many of you guys have looked at this and say, Chad, are you kidding me? You're showing me sources of power in series. There are two ways, guys. Remember the loads. The loads, you can put the loads in two ways, either in parallel or in series. The loads. 99% of the loads are in parallel because the voltage stays constant for them. They are made to work on a voltage that's constant. Now, the sources of power, you can put them all source of power. The source of power, you can put them in series and parallel. The very common concept, guys, for a voltage in series, to put power in series is batteries. Now, take this. Some of you might say, Chad, when are we going to see this? Data centers. When you guys walk into a data center and they have room, we will be walking into a room full of batteries like this, 12-volt batteries tied together in series to get you the voltage, in parallel to get you the current. That's what they're talking about. This concept is coming back as in a data center. So you're going to enter with, instead of 2 volt, with 12 volt here, and 12 volt here, and 12 volt, and 12 volt. So that'll give you 1, 2, 3. Let's see another 12 volt here. Well, let's just say 1, 2, 3, 4. That will give me what? 40 times 2, 48. 48 volt. So that system is 48 volt. 48 volt, okay? 48. Now, imagine multiply this by 10. That will give you 480 volts, right? Imagine 40 of these, right? 40 of them. I have 1, 2, 3, 4 times 10, 40. 40 of these 12 batteries tied together in series. They get you 480 volt. That's how they do in data centers. Now, this string will give you 10 amps. 10 amps. Okay, so I got only 10 amps. I'm just throwing this number. Now, suppose, Rob, you want another 10 amps at the same voltage. What would you do? Thank you. Absolutely. You draw another line right here. Come over here, and you put all your batteries right in here. Tie it. So here you got another 10 amps, and so coming out of here. So this and a 10 amps coming out of here. Now you change this one to 20 amps. If you need another 10 amps, what do? Another string, and a third string, and a fourth string. That's what they do in data centers. So that concept is very powerful. Yeah, simple. Yeah, you guys analyze it. Yeah, you know how to do it. But it's very, very powerful. We put batteries in series to add up to a certain voltage, because that's what our equipment work at this voltage. You keep adding them to match your equipment. If your equipment work at 480, 600, whatever. So you match your equipment. After that, at a certain amp, say 10 amps, 20 amps, every string will give you 20 amps. Now if I need more power, what do? Add another string, and a fourth string, and a fifth, and so forth. So this concept, putting batteries in series and then paralleling the strings. By the way, this is series, and this is series, and together we put the two strings in parallel. Can you guys see that concept? I return to this concept when you go to the commercial too. The worst thing that could happen to you, though, is to take a synchronous generators and do that to the synchronous generators. Put them in series. Oops. You wouldn't get a whole lot. This is for the DC concept. In generators, we put them in parallel. You hear at work, they say, we're paralleling three generators, 2 meg each. Putting them in parallel. Synchronous generators, we put them in parallel. Batteries, DCs, and so forth, we put them in series to reach the right voltage, and in parallel to reach the right amp. And by the way, by reaching the right amp and voltage, we're after what, guys? We're after power. We're after power. So when I say voltage multiplied by current, so look at this. I can reach my voltage by putting them in series, and I reach my optimum current by put the strings in parallel. Both ways will give you more power, and that's what we're after. Power. The key word is power. Voltage by itself is meaningless. Current by itself is meaningless. Together, they make something very powerful. It's called power. Higher voltage, higher current, more power. I mean, very, very great concept. Higher voltage, higher current, more power. And that's what we're fighting all over the world, guys. Over what? Power. From the oil all the way to everything else. Power. Okay, series connection, guys. I told you about. We will talk about this one more as we go into series connection. You can put. We can put the coils in series. I don't know if you guys can see that. Some of you might not see that this is in series up to this point. So you can series connections to get you a delta, and then bring a phase to each one of them. So that's another concept where, again, you can series to get you higher voltage for transformers, generators, and motors. Parallel circuits. Parallel circuit is the one that you cannot live without. So rules of parallel circuit, very quick, and you're not going to hear Chad talking about this ever after that. Rule number 1, I'm going to write them right here, guys. What's going with the voltage? V is constant. Maybe this is the single most important thing about why we adopted in the world the parallel circuit for power transmission. Because the voltage stays constant. Every time you add, I turn the light on and off. What's going to happen to the voltage across these plotters and printers? Stays almost constant. Fluctuates within 5%, up and down, but it stays constant. It's not going to double or triple or cut by half or cut by fourth. Okay, so rule number one. Rule number two, my friends, is current I total equal I1 plus I2. So the current adds up. That's why when you guys start adding all the current up until you come up with, oh, I need a 100 amp panel, Chad. What do you think a 100 amp panel? You're adding all the amps in the going to add up right here to 100 amp panel. What's the voltage? Constant, 28120. Voltage constant. It's a parallel. This is a parallel system, power system. Number three, power. Power total equal P1 plus P2 plus P3. The power adds up. Every time you plug one of these printers and you start working it, you start consuming more power out of the system. Okay, 1, 2, 3, 4. We have multiple paths, as you can see. Multiple paths, if I can spell that one. And the last thing is, guys, an impedance or resistor R, and I'm going to put them in a 1 over R total equal 1 over R1 plus 1 over R2. The sum of the reciprocals of all the impedances in the circuit equal the reciprocal of the reciprocal of the total resistance. This is one of the most important concepts, guys. And again, you guys have done a lot of calculation for this, so I'm not interested in the calculation, I'm interested in the concept. Concept number one here, very important, constant voltage. This is where you get your 480 volt, 208 volt here, 240 volt here in the US, and either 480 or 208. It can't be the same. The panel cannot be the same, 208 and 480 at the same time. You have to choose constant voltage. The second concept, guys, importance is the more load you add to the system, the less the impedance of the overall of the system. Beautiful. So the more, imagine, guys, the more we add, this is a major concept in the transmission distribution power. Major concept. Every time you hook up a city in the state of Minnesota to the grid, for the most part, theoretically, the overall impedance of the grid goes down instead of going up. If you apply the same concept to the series circuit, every time you hook up a city in series right here, the impedance, overall impedance of the system goes higher. Who cares about, the question would be, Phil, who cares about the impedance? Well, guess what? The impedance is that barrier between me, the generator, and you, the load. So the more impedance, the less I can push that power directly to you, right? So the less impedance in the system, the more I can push my generated power to you. So this is major concept, major concept, major concept. So these two guys are the most important concepts in the circuit, and that's why we adopted the parallel circuit for everything they're going to do with your friend Chad. All the branch circuits, all the feeders, all the service intrinsic conductors that you guys have done with us, these are all parallel circuits. All of them are parallel. Any question, guys, about the parallel circuit? As I said, I'm interested in the concept because you have done all the analysis, guys, and so forth. And my interest is not the analysis. My interest is the concept at this point. Questions? Any question, guys? So that's the most important thing about the concept. As I say, we talked about everything basically that we adopted is connected. You can look at all these loads, all these receptacles that you can see are connected in parallel. The voltage stays constant. The current fluctuates. And I don't know if you guys can see that one here. Where am I here? Right here. So look at the current. The current stays constant. The voltage stays for the most part across all of them. 120, say 120, 120. But if this load is to turn off, so I turn this load off, gone, right? So I lost then 15 amps. Then this changed into what? 10 amps. So what happened to the current? Goes up and down with the load. And what stays constant? The voltage. That's the concept that we designed it. First, believe it or not, there are equipments that work on the opposite. The voltage stays constant, a certain equipment, and the current fluctuates. I'm sorry, the current stays constant, 10 amp equipment 10 amps, but the voltage can be 120, 300, 20 volt, you know what I mean? But we don't want to go even there. Can you guys see how the voltage stays constant? The current fluctuates. And vastly fluctuates, doubles, triples, quadruple. on the system. It's not just fluctuate 5% and 10%. Lighting circuits. These are your lighting circuits that you design with Chad. The only thing that you can see that we put in series with the equipment. What is this? Control. Series becomes very big with control. The only thing that we did in series with the light here is what? Control. If you don't care about turning this light on and off, these switches, unscrew them, open the window, throw them out, and the circuit will continue to work fine. But you can't control it though. So these are for control. Practical use. Okay, smoke detectors. This is another concept, guys, where you use a parallel for control, a parallel circuit for control in a smoke fire alarm system. If I have a heat detector or a smoke detector or a pull station, if I have fire here, if I have fire in this room, I need to be able to detect the fire in this case and make a decision by if there's a heat detector. There's a heat detector right in the ceiling. The temperature reaches a certain limit. It closes this contact, and the alarm goes off. And this will close. The alarm will go off, and get the heck out of there. So it made a decision individually. The smoke detector can also do the same, as well as the pull station. If nothing happened, and you see a fire right there, the first thing to get out, pull station, pull it down. You basically close that one. So can you guys see? These are control devices, and they're put in parallel, because we want the circuit works in parallel. A parallel means every one of them can make the decision to activate the system. In series mean all of them have to agree before the system is activated. That's a control concept. Chris, you've done a lot of programming. That's a major programming control concept. I have you guys here. Do I want all of you to agree to change the test? Right? That's series circuit. Or do I want, if one of you agrees to change the test, I'm going to change it. That's a parallel circuit. Put you all in parallel to make a decision. Does that make sense? Control. Major concept of control. Okay, practical for parallel circuits. Again, back to the parallel and the series circuit, guys, are used with power equipment, transformers, generators, and motors. The problem with the parallel is, if you parallel 120 volt and 120 volt coils, put them in parallel, you get 120. So you can tie them to 120. If you series them, you can tie to 240. They add up when you series them. When you parallel them, they stay the same. 120, 120, you hook up to 120. Who cares? The question always in my mind, who cares? They allow you to manufacture equipment that can run at dual voltage, motors, generators, transformers. Is that a big concept or not? It's great concept, guys. It's a great concept. It's like I always think of it as between SUV, between a big van, minivan, and a car. Gives you the concept of both, so you can utilize it. That's probably the parallel series circuit is the same thing. Utilize it in different applications. 2 voltages, dual voltage equipment. Any question, guys, about paralleling the coils? As you can see, the coils right here is parallel. And the coils, this set of coils are parallel with the other set of coils. There's 2 stars and parallel to get you a lower voltage. So that's a major concept. Parallel circuit voltage. Voltage stays the same. This is why we choose it. Otherwise, good luck. The most important concept of it. The resistor, the impedance. You guys did a lot of resistors. The impedance of the overall of the system goes down by adding loads, theoretically, but there's transmission line issues, but it goes down. So that's good news. That's very good news. Power is still power. Power circuit, guys, still the same. It adds up. The power is a big deal, guys. I still the same thing. The power in each one of these loads. R1, these are all loads. The power adds up. Always the power adds up. Always. Every time you turn one of these lights, it will consume power, adds up. Doesn't matter if it's series or parallel circuit, by the way. The only thing that's coming between parallel and series circuit is what? Every time you turn something on, you consume more power. And it adds up. Otherwise, why do we need these two circuits? They're not consuming power. Resistance calculations. And you guys, you know how to do the resistance calculation for parallel or series circuits. You take the 1/16, 1/13, 1/36, and you do the math. By the way, the electrical calculator that you guys have has the capability of doing that. We'll do an example just for the heck of it when we get it. But I'm not going to do examples on product over sum is the single most important one, guys. Product over sum. If you have two resistors, you multiply them, divide them by their sum. That will give you the total resistor of the system. Unless you're doing engineering work, an impedance and a resistance is not a big concept in the design unless you're doing some engineering work. So these are the equivalent resistance. Okay, you guys have done that. The total resistance sum over is the sum over the product over the sum. When you have two of them, this is maybe the most common one that easier to use, right? Take multiply and divide it by 2. And again, am I cutting you guys short by not going over this? I hope this you've spent 1 quarter with us doing all this stuff. This is just a quick overview. And again, my intention, if you have more, you take 2 at a time, like you guys done with Ryman, and 2 at a time, and simplify the circuit. Reciprocal, you can do the reciprocal. Okay. All right, go ahead. And I'm going to move fast through these. All right. Again, assuming that you guys, we have done that before. This is quick review. Parallel circuits, guys. Parallel circuit supply batteries. Now, this is major concept. We can put also batteries in. Do you guys remember? I want to stop right here. What did we say we put batteries in parallel to get us what? More what? This is 10 amp. This is 10 amp. What did you get here? 20 amp. Okay, suppose this was a 12 volt, and this is 12 volt. Look what happened to the batteries. It becomes 20 times 12, 120. That would be 240, right? 240 volt VA. Voltage.
Isn't it 12?
1 second. 12 and 12 in parallel. Each one of them got 10 amp, 10 amp. That will make it 20 amps. When I'm going to find the power. So 20 amps times 120. 10 times 120, 20 amps times 12. 120 plus 120 is 240, right? So I got 240 volt amp power. That's what I got out of this system. Now take this out of the equation. Take this out of the equation and do the power for this. It becomes 10 amps because I got one battery out, multiplied by 120. What do you get? 120 volt. So why the heck did we put 2 in parallel? To get us more power. The key point is power. So these are for these guys are for DC. The same thing, guys. What we do is we bring a gen. Here's generator 1, generator 2, and we tie these two generators together, and we bring them into the system. I have 2 meg, add them up together and tie them to a system here, and this system capacity now is a 4 meg. That's why we parallel generators. And these are in parallel. These 2 generators are in parallel. I'm going to just put that one. These 2 generators, exactly like these 2 batteries, are in parallel. Doubles the voltage, the power. Almost always, Rob, when we parallel generators, they're almost the same, almost always the same size. 2 meg with 2 meg. Any question, guys? Why we power? The same thing with series. Why did we series to get more power? The problem, the only difference here is the voltage stays the same. See the voltage, 12 volt. I'm sorry, should be 12 volt too. 12 volt, 12 volt. And this is, say, suppose this is a 13.8K, and this is 13.8K. The system here will continue to be 13.8K kilovolt. They're in parallel. Voltage stays the same. Any question, Nick? That's what Michelle Erickson is doing when you have parallel generators. That's exactly what they're doing with them to get you more watt always. Power. Yes, sir.
Kind of a top question. If you peak paralleling, like, let's say 4 batteries together, does that potential harm the electronics in the vehicle? Because I know they do it with jump start.
Yeah, there's a limitation on yeah. There's other factors that could happen. I don't know what the limit of how many you can put in parallel, but yeah, there's a limitation where other issues, fluctuation and so forth, that could affect you. But yeah, you have to consult the manufacturer of the batteries, and because they're source. The same thing for generators. You start putting generators, believe it or not, there will be a circulating current going from one generator to another, and there's a whole lot of control system that looks at when you put 2 generators in together, they want both of them to push the power at the same time, push this way and not circulate power from one to another. So there's some control have to be done to make sure the system works the way it's supposed to. Good point. Did you say 4? If you add 4 or more?
Yeah, I just think it's like, how long are they if your car is dead and jump starting and get more voltage in your computer system in your vehicle? And that's
You jump your car. No, one car to one car, I don't think it should be. Again, I'm not an expert in the car batteries, but you do it all the time. Because all what you're doing, you know, when you parallel, what are you giving? You're giving amps. You shunt more. You put because that 10 amps here is probably 5 amps. It's dead. You can't push 5 amps. Start the oomph. So you're giving it oomph.
Yeah, but then like on my vehicle, my Jeep, I just had a bad connection. My battery was fully charged. It's like corrosion.
Yeah.
So if you wiggle it, you'll get the spark and it'll be a full battery.
High impedance. So what you did is right in here, you have a high impedance here. So you're choking the voltage that's going to, you're choking the volt. If it's a 12 volt, you lost in that impedance, say 4 volt. So your coil is getting what? It's getting 8 volt, and you're trying to push current at 8 volt, and you can't start your alternator, right?
And I was thinking of pushing all these double amps to all your little fuses in where they're only rated for
There are two types of currents in cars, and again, I'm not an expert in cars. One is the charging, the cranking, the one that start that's a high amp. It goes 600, close to 600 amp at 12 volt. But for how long? For how long? Otherwise you burn it, right? For a very short amount of time. So your fuses are able to handle this amount of current for a very short amount of time. Now, if you continue doing that, what's going to happen? You're going to burn it. You're going to burn your equipment. So for a very short amount of time, they can handle a huge amount of current. But when the car is up and running and you turn your radio and turn all this stuff, they're running on your batteries, which is being charged by an alternator. If you start putting a heater and start putting in your car plugged in and other things, your fuses will blow because you're running. You're at the stable condition, right? When you start, that's just a transient condition. To start the engine, got a huge amount of current to get oomph in rush. And start it. Now you start it, everything is fine, it's running. Now you're going to run loads on it. So, any comments, guys? Good stuff. But this batteries in parallel, guys, is a very major concept in data centers. Major concept in data centers. Okay, series parallel circuit. Now in the real life, guys, your circuits are going to be series parallel. Here's what's going to be series. What's going to be series, guys, the transmission line and the conductor's impedance, that's series, always in series in a circuit, and the control circuits for the most part. The load's almost always, 99% of the time, your load is always in parallel. So anything in series is going to be basically transmission line, distribution lines, and so forth. Okay, so if you're looking at this system here, this is 30 megawatt power plant. This is my power plant, and these two are transmission lines. This is Richfield, and one more. We continue with the transmission line here, and we went down to from Richfield. Where we're going to go down to? Give me a city. Let's go or up to St. Paul. Can you guys see where this is what the real transmission system is? You bring the power from Becker, 30 megawatt, and you shoot it through the interstate, electrical interstates, so-called electrical grid, shoot them through the transmission line, you reach the city Richfield, you fed Richfield, and all the city Richfield, all the homes, and then you continue shooting it all the way till you reach St. Paul. So where's the loads? Where are the loads? The loads are the cities. What are these in series? Can you see this, the stuff in series? The stuff in series is in reality what? Your transmission lines. Go down a little bit lower to our level. Where's the series? The series is resistance of the cables. The parallel, the load, the parallel stuff is the load. So did I drive that one, guys? Good. So that always the series stuff is most likely is going to be the impedance of the circuits. Okay, how do you analyze this circuit, guys? You take them two at a time. You're going from series to parallel to series. And I'm not going to go through the whole analysis because you guys have done it enough, I believe, with us. I just want to emphasize the power concept of it. Okay, power circuit. All right. Okay, so, and you guys can look at these to refresh your mind. All right, let me see what we were working series parallel circuit. All right. Okay, I'm going to go, guys, continue with the voltage resistors. The analysis, I trust that you guys know how to do the analysis because we've done them a couple of times. Okay, I'm going to go directly now into multi-wire branch circuit, aka polygamy, like Chad said yesterday. Multi-wire branch circuit, guys, is when two, as you can see, everything in parallel. I want you to understand these two, all the loads are connected in parallel, except you're utilizing two voltages. You're utilizing two voltages. So you're utilizing one line of voltage is coming here, and a second line of voltage, as you can see, is coming from the other top. But they are all referencing the same, they're all going to the same reference. All going to the same reference. Multi-wire branch circuit. A couple of things about multi-wire branch circuit. You almost always have to come adjacent. This will be 1, 2, 3, 4. If you don't know that, please remember it's always from two adjacent odds or two adjacent evens. Here's the odds on the left, even on the right. Always. And the voltage between them 120, 240. If I want to make this three-phase, right? All what you have to do, make the system three-phase, a third one here. And the voltage that we use in the US three-phase, it becomes 208, and this voltage actually continues to be 120, just because these are the utilization voltage. Here's a multi-wire circuit. Multi-wire because they all share the same neutral. You can only have up to 3 hots with one neutral. 4 hots with one neutral? No. Feeders, branch circuits, and service. Always up to 3 hots with one neutral. Any question, guys? In a single-phase system, if this circuit pulls 10 amps and this circuit pulls 10 amps, the one coming here is 0 amps, as you guys know. The way the single-phase system works, if 10 amps going, they go against each other, magnetically, they cancel the effect of each other. That's what they did. The power have reached the destination. So you have 10 amps here, I have 10 amps here. What's going to come back right here, can you guys see right here back, is 0 amps. Why? Because by design, magnetically, these systems, these currents are going opposite direction. They neutralize each other as they reach the destination back at this point. Who cares? Then the multi-wire branch circuit is not carrying as much current.
So if you put a clamp on the neutral,
you will get 0. There's some harmonics that's creating, not in residential, when you go to resistor, 3 phases harmonic that could, if the equipment is electronic, it could screw up the value for you. But if your system is all 100% resistive load or motor load, no harmonics, nothing electronic in it, you'll get a 0. And who cares, guys? Beautiful. If you get a 0, then it's not, no losses in voltage, no losses in the power, nothing. Any question, guys, about multi-wire branch circuit? Always two adjacent odds or two adjacent evens sharing one neutral. Okay, neutral calculation. You guys are going to be doing neutral calculation for us. Here's a neutral calculation for that. Here's a three-phase. This is your single phase. We're concentrating. This is also single phase from here to here, at least. If the current here is 100 and the current here is say 250, this current will carry the difference between them, right? 100, 200, 250. The difference is 150. Yeah. In this system, the current here is 35 amps, and the current here is 50 amps. The difference between them is going to be carried, what is that, 50, 35, 50. It's going to be 15 amps. Any question, guys, about these? These are single phase. Yes, this is a three-phase system, but that part of it acts exactly like this part. Delta center tab, this part, just that part, acts exactly like a single phase. This is what they call it, the neutral point. You guys are familiar with the neutral point? The point that ties the bottom, the conductor connected to the neutral point, which is the point right inside the transformers in the coil, as you can see right in here. And it's grounded, always grounded, going to Mother Earth, always going to Mother Earth. Any question about the two systems on the side, guys? Neutral point and neutral conductor, or grounded conductor, fancy name for neutral conductor, we call grounded conductor. What's the advantage of this? It gives you two levels of voltage. So that's the only reason why we have grounded system, guys. Well, one of the reasons. Stabilizes the system is one. The other one is to get two levels of voltages. Who cares? I can have a lower level voltage here, safer for my kids to play with, and a higher voltage up here where nobody can reach it, so I can run my air handling unit at 480 or 208, three-phase. Isn't that good or what? Great, because remember the rule of series circuit, a parallel circuit, the voltage stays constant, so I have to make an effort to change the voltage, major effort, as in having a system that changes the voltage. Because the voltage stays constant. You have to make the system change the voltage. Okay, for a three-phase system, guys, this is your 208/120 volt, or your 480/277 volt, right? Any voltage to ground, 277 or 120. And if this is 100 amp, and this is 100 amp, and this is 100 amp, what do you guys expect to come back here? 0 amp, right? Expect to have a 0 amp. In a resistive non-harmonic load, resistive non-harmonic load, you expect to have a 0 amps. Great example, I have a three-phase panel right here, guys. I grab a feeder and feed 10 lights, 10 lights, 10 lights. I expect to get on the neutral, multi-wire branch circuit, I expect to get in the neutral 0 amps, or as close to 0 as you can. Because of a harmonic now, you'll get some amps. Because of harmonic, which is a different story. But if they were heater resistive loads or inductive, completely inductive loads, you'll get a 0 amp if they're balanced. Any question, guys, about the neutral point or the grounded conductor? Why do we care about grounded conductor? Two levels of voltages. It's the most important thing. One level safer, lower voltage. One level higher, phase to phase. You can burn equipments at a higher voltage, which is less safe but more efficient. The higher the voltage, the more efficient the system is, but the more dangerous the system is. So I can't put 480 here and allow my kid to plug in an outlet in the 480. You know, any mistake at 480, you're dead. Versus any mistake at 120, you have a chance to survive. Otherwise, we will make everything, all these outlets, all these equipments you can make in 480, the printers, the plotters, everything else. The problem is you want to make it 480 more dangerous, and you have the equipment have to be more robust to handle the higher voltage. Any question, guys, about that? Any question? So that's what I want to mention here. Neutral conductor calculation with neutral point. Okay, neutral point coming between the three. You guys looked at these. We looked at the midpoint. Grounded conductor is the same as a neutral point. Gray or white. You guys remember that? Talked about two-wire circuit. Two-wire circuit. I'm going to give you guys a break in a second, I think. So if you have a two-wire circuit like this, guys, if the amp's 20 here, what do you think is going to come back? 20. Now, if I put right here, another 20 here, what do you think is going to come back? 0 amps. Cool. Now, In a three-phase system, the same thing. This is single phase. In a three-phase system, if you take single phase with a neutral, 20-20. Now, if I add another resistor here and put 20 amps, that's not going to add up to 0. This is the most common mistake. In a three-phase system, if you put 20 here and 20 here, you will continue to get 20 here. In a three-phase system. In a single-phase system, if you put 20-20, you get a 0. And I want to remind you, here is the system, the transformer that I started with. Here is things about multi-wire branch circuits. Like we said, if your system is balanced on a single phase, 20 amps add up to a big fat 0. This is how graphically, guys, just FYI, why does it add up to a 0? Because the current that goes in here and the current that goes in here are 180 degrees out of phase. 180 degrees out of phase. If you imagine your car and my car are going against each other like this at 60 miles an hour. You go 60 miles and I go 60 miles and you're not moving anywhere. You basically adding up to 0. And can you guys see that when this current reaches this point, this reaches this point negative, so they cancel each other to a big fat 0 right in here. 0 So that's just a graphic. But why do they act this way, Chris? Because the way we design the coils. I can make these coils act this way, or I can make them act like in three-phase. The other way, though, here's a three-phase system where you start with 180 degrees. How did they do this? By the way they design the coils in here. By design, the way they design the coil. Any question, guys, why in a single-phase system it adds up to a 0? Cool? If they are balanced, if they're not balanced, it adds up to the sum of both. On the grounded conductor, if it's a three-phase, as I said, if there are difference between them, 20-15, it adds up to the difference, right? So that's also, we got that one. Grounded conductor. If it's a three-phase system, single phase, let's go back into. Okay. Now, the thing that they always warn you guys, as here's L1, you see, if you put L1 and L1, remember how this will be 1, 2, 3, 4, 5, 6. So that will be, if you take 2 and 4, 2 and 4 are L1 and L2. 2 and 6 are not L1, 2 and 6. These are L1, L1. Both of them are L1, L1. So if you do that as a multi-wire branch circuit, you basically adding them up. So if you have a 15 amp plus 15 amp, it adds up to a 35 amp. Are you guys with me? That's why multi-wire branch circuits are so dangerous, because anybody can, well, you have to treat it properly. You can't just take any circuit, add it to any neutral, and call it a day. A lot of people, guys, open a box and grab a circuit. Okay, here's a neutral, title neutral. It works, but you could overload the neutral here. They have to be from two adjacent odds or two adjacent evens in order to qualify as a multi-wire circuit. By design, if you do it this way, they cancel each other instead of adding up each other. In this case, look at that. They add each other's up. Instead of being up and down, and where they cancel each other to a big fat 0 here, in this case, they're all coming from the same leg, and they add up each other. Okay, cool with that?
Both need to be resistive loads for this to work. If you have an inductive load on one and a capacitive load,
They will add each other's up. They will add each other's up. If they're not resistive load, they will continue. The rule's still the same, except they add each other's up vectorially. So you start working with an angle. It gets more interesting. You start adding, still add up. But you guys know, let me ask you this. Now that you open this subject, what's 1 plus 1? Chad, that's a hard one, right? 2, right? 2. 1 plus 1 is 2. No, not always. Take this. What's 1 vector plus 1 vector with 90 degrees? We have two vectors, and they are 90 degree, 90 degree. That's, I hate to do that. Here's 90 degree. This one is at 90 degree with this one, vectorial addition. I'm just going to give you a taste of the engineering here. So here's my one here, and here's my other one here. When you add them up, and I know you did it, guys, because you did Pythagorean theory, this will 1 squared plus 1 squared. This equals square root of 2. What's the square root of 2? 1.4 and some change. So that's something you can take to the bar this weekend and tell them, what's 1 plus 1? It depends on the system that you have. This system, that's just to answer your question. This system is called complex numbers. A lot of you, anybody ever heard of complex numbers? Complex numbers. There are two sets. The most of us guys finished our calculation with numeric with the whole numbers, right? Whole, fraction, real numbers. Real numbers include everything. After the real numbers, there is one set of numbers that a lot of you probably have never even heard of. It's called the complex numbers, where you can add numbers with an angle. Any angle. So long story short, that's why that's a phase of the engineering where you start adding 1 plus 1 is no longer a 1. 1 plus 1 is 1.4 depending with an angle. You have to tell me 1 plus 1 as real numbers. Yeah, 1 plus 1, if they have an angle difference between them, it doesn't equal 2. So that's why all this stuff that you can see. And I'm going to stop on that one, balance systems. A few things about the balance systems, guys. A three-phase, look at the side, on the other side, if the system is balanced, 0, 0, 0 coming out of them. In single phase or a three-phase system. Okay. Okay, 3-wire 120. Just a few things. They subtract each other's, as we said. And I'm going to keep going all the way to 277. Okay, now, if you say, this is where I want to just take a few seconds, guys. What happened if you have here's phase A, phase B, and phase C. Phase C is off, and you put a 20 amp plus 20 amp on phase A and B. It's a three-phase system. Have you guys seen the neutral formula to calculate the neutral for three-phase? If you haven't seen this formula, then the neutral formula says if you take the square of phase A, add it to the square of phase B, add it to the square of phase C, add them up, subtract from them the multiplication of each one by the other. AB, BC, and AC, or L1, L3, and so forth. Subtract, and that will give you the neutral if you have no harmonics. If you have harmonic, it will be slightly different. Okay, so if you guys apply this rule to it, you're going to see if you only have using two phases, this current right here is going to be at 20 amps. I can't emphasize, Tom, my friend, I can't emphasize. These are a three-phase. The system is what? I can't emphasize. A system is a three-phase system. If it's a two-phase system, and not, if it's a single-phase system, two hots, 20 plus 20 equals 0. Because they're going 90 degrees against each other. 20 plus 20 equals 0. In a three-phase system, 20 plus 20 equals 20 when you add them up. When you add them up because of the angle, remember that complex number that we were talking about? You can prove it by doing the complex number. You can add them up with an angle of 25 degree, 120 degree, you can add them up. That's this coming from adding the complex number. If it's complex, because it's coming from the addition of complex numbers. Add them up, and you come up with a 20 amps. Any question, guys? Here's what you need to know. In a three-phase system, if you have one phase on, then the neutral will carry the same as the phase. If you have two phases on, then the neutral will carry the same as the largest of the two phases. Or you can do the formula. If all of them are on, meaning I want to balance this system, so no problem, Chad. Add another resistor right in here, another 20 amp. What do you guys think with the current here is going to be? 0 amp if you have no harmonics. If you have no harmonics. Okay? Does that make sense, guys? But this is, and I don't want you to think that we're going to disconnect the phase. Here's how a phase is. Well, these are coming from three phases. Here's phase A, it's phase B, and phase C, right? So if I turn these phase A, B, and C, so I'd look at phase, let's see, let's go on that one. So phase A, B, and C. If I took C and turned C off, now I have this situation they're looking at. Two phases on. It doesn't have to even go that far. You can turn the light. Light is on. See that light? Turn it off. Now that could be in phase A by itself. you phase C by itself, and you get yourself the situation that I'm looking at. Any question, guys, about how to use the formula, though? How do you use the formula? You square L1, square L2, square L3, which is 0. Then multiply L1 with L2, L2 with L3, and L1 with L3. Add them up, subtract them from the sum of the squares of all the L's. Now, Phil, my friend, you're looking at me and say, Chet, are you kidding me? Am I going to be memorizing this one? You can memorize it, no problem. I do memorize it. But for my own test, it's open ugly and open formula. So bring that formula with you. You're professionals, guys. You're sitting and working on your field. All your formulas in front of you. Do the answer. Any question? But do you guys know how to apply it? Everybody knows how to apply it. This is algebraic formula. How to plug in numbers in it. Any question about that? Any question, my friends? And it's also in DeWalt. Okay, so that's if they're not. Again, remember, this is only for 3-phase. Okay, now the same thing, guys. Look at that. I have 100. I have 100 here, and 100 here, and 50 here. Plug them in, and the answer will be 50. It has nothing to do with this 50, by the way. It just happened to be. The answer for the neutral is 50. 100, 100, and 50 here. The answer here is 50. You have to plug in the numbers. Now, if I make this 100, what do you guys expect this one to be? Big fat 0. Any question about the neutral? Any question about the neutral? And you guys have all these graphics. Multi-wire branch circuits. Okay. Reduced conductor. Okay, so there's a lot of advantage, guys, for a multi-wire branch circuit. That's what we're doing. I can tell you 2 things about multi-wire branch circuit. Instead of having, if I have a 3-phase and a neutral, if I don't have a multi-wire branch circuit, I have to have 4 conductors. I can have 6 conductors. I save 2 conductors. A lot of money. Number 1. Number 2, guys, voltage drop. You can save in voltage drop. You can save in conduit size. You can save in a few other things. So it has a really advantage. A big advantage for, I always say when we go commercial, you always use multi-wire branch circuit, use them wisely though. Voltage drop. Okay, I think I'm going faster than my machine can go. Faster than my machine. So voltage drop, guys, also is a big deal because you don't have any current in the neutral. You don't have any current going on a neutral. And I don't want to use that one for 3-phase because we have a different voltage drop. The problem with voltage with multi-wire branch circuit, guys, as you all know, if you lose a neutral, I have a picture here. If you lose a neutral, the problem with multi-wire branch circuit is this one. If you add them up, look how if you misuse it, it adds up. And what happens if you lose a neutral too? There are 2 dangers of multi-wire branch circuit. If you misapply it by taking one, this is 1, 2, 3, 4, 5, 6. You've taken 6 and 1. 6 and 1, that's L1. That in this case actually, 2 and 6 here. If you took 2 and 6, that would be L1, L1. You add up the neutral, you have just burned your neutral. Well, not really been burned, but there's a hazard of burning your neutral. Okay? If you guys open a panel sometimes and you see the neutral is burned, that's probably part of it. Or harmonics also cause this issue. That's a hazard, but we are smart. You're going to tell me, Chad, we're smart not to do that. We're designers. We don't, but we always do let me see here. We always put them in 2 different adjacent odds or adjacent even. Let me see here. The last one I want to do, what happens if you open a neutral? Come on, bud. Okay. So here's this is a big possibility. Did they tell you about my story with the fan and the light? Did they tell you that story, guys? I always tell it. I was working in a motel here, wiring, in Minneapolis. So working by myself in the basement. So doing electrical work. So we're adding a couple of lights and receptacles and everything else. And I want to steal from an existing circuit and add, I think, can't remember, 2 lights and switch or something. I'm not pulling a new circuit, adding to an existing circuit. There was a box, Chris, box full of wires inside them. So I wired everything, false ceiling like this. Everything is wired. The last thing I want to do is tie to the circuit to steal power to that extension of the branch circuit. Now, the way you should do that, turn the power off and tie to it, right? But if you turn the power off, you can't see there, and I'm lazy because I don't want to bring light, and so mistake number 1, being lazy. End of the day, I just want to get it done. So, and I work when things hot. So, the first thing you do when you tie to a circuit hot, which you shouldn't do, you should turn everything off and tie it. If you are to do it, you put the ground to ground. First, you ground the system. I ground it. The second thing I do is always put the neutral. The last thing, because you're tying things hot, remember, you're going to be very careful. Last thing is you tie the hot to the hot. I put ground to ground. The second thing I want to do is what? To do them, your 3 wires, you're going to unscrew the wire nuts and put 1 wire underneath it, right? Good for the ground, no problem. For the neutral, there's a bunch of wires, white wires under 1 wire knot. Unscrew that wire knot, not knowing, I should have known, that it's a multi-wire branch circuit, Chad. And that multi-wire branch circuit was there. The minute that I unscrew it, they went open. So what did they do? I opened the neutral right here. When I opened the neutral, there was a fan right here, and a light. Exactly the same scenario. I'm not kidding you. A fan and a light. The fan and the light happen to be on the same circuit. So the fan in the corner, exhaust fan, got lower voltage, supposed to get 120, say it got 60 or 80 volts, so less volt. It was running at the time. It kept sucking more current to compensate for the lower voltage. That's what motors do, guys. They're dumb. Instead of saying, you don't give me enough voltage, I want to stop right now. No, they start sucking more current to compensate for the loss of the voltage to maintain the same amount of horsepower that they're supposed to do. So start sucking more current. What happens when you start sucking more current in the windings? Start smoking. Within seconds, big ball of fire came from the fan on the corner. And that light over here went so bright. I'm standing on the ladder, on the step ladder. I can't believe it. It's so bright right in front of me. Because it got what? It got a big chunk of voltage. It was rated for 120, got 160. So bright. Luckily, because of the fire in that fan, it shorted and the circuit breaker took the circuit down. Otherwise, I could have lost my house that day. Burn a motel. Are you kidding me, man? So that's how danger. When you guys, I can't emphasize, if you are a wannabe electrician or you're an electrician, when you mess with the neutral, be very careful. Always, every time you see the neutral, it's more dangerous than the phase. The phase can give you a shock, and if you're careful, if you open the neutral, you create fire, no question asked. No question asked. So when you guys go to the panel right here, it would be easier to unscrew this wire here hot than doing this. If you unscrew this one, the neutral, you just burn these equipments. Imagine your plasma TV, and now so there's plasma TV here, and this is your garbage disposal. Burn both of them. And the circuit breaker, Phil, will do you nothing. So what happened, guys, as you understand is, these equipment are rated for 120 volt. They're rated for 120 volt, and all of a sudden, you put them in series. Bad news. We don't put power equipments in series. Remember, we just talked about series. Bad news. You put them in series and you said, okay, here's a big chunk of voltage across you. So the biggest, fattest, highest impedance one will hug most of the voltage, which happens to be the light. And the smallest, skinniest piece of equipment will take lower amount of voltage, so they can add up to what? The source voltage. They have to add up to the source voltage, as we all know. And what happened to both of them? This burned because of overvoltage, and this burned because of overcurrent, which is caused because of undervoltage. Overvoltage, substantial overvoltage or substantial undervoltage are as bad. Okay? Any question, guys, about this? So, unreal. A real problem. This is a single phase, but it could happen in 3-phase. You could take the neutral here of 3-phase circuit, and you impose a 480 across multiple loads. What happened is if that was a 3-phase, look at this. Suppose that was a 3rd phase here, let's just say there was a third phase here. Now, if you get rid of the neutral here and all the same size, if you get the neutral and all of them are the same size, no problem, still balanced. If you get the neutral and the impedance of them is different, the highest impedance will get the highest voltage, it will smoke, and the lowest impedance will get the lowest voltage, and if it happens to be a motor, it will smoke too. Any question guys about the danger of multi-wire branch circuit, three-phase or single-phase? Now this has nothing to do with the design maintenance. You guys will design a good system, but as you troubleshoot, so I can't emphasize from my own experience and yours guys, always be very careful when you open a neutral, very careful, especially in a residential or commercial building. Very careful when you open a neutral. Okay, almost done with that one. Okay. Any question, guys? Any question? So what the code says, guys, for multi-wire branch circuit, if you have a multi-wire branch circuit, they want you to pigtail the neutral. Because anybody knows why in a multi-wire branch circuit they want you to pigtail the neutral? Because if you attach the neutral in and out, if you move this device, what happened to the neutral here? You lost the neutral. You have an open neutral. You can have open neutral in the panel, open neutral in a J-box, or open neutral right in the device. So if you are wiring with multi-wire branch circuit, the first thing you need to do is pigtail the neutral. Must. You can't land the neutral. So for example, you can't get the neutral in and the neutral out if it's a multi-wire branch circuit right at the device. Because if I am to replace this device, what's going to happen to the neutral? Open the neutral. The worst thing that could happen to you when you open neutral is you burn equipment. You don't short. If you short circuit, that's beautiful. Short the circuit breaker, but burn equipment without any of these wake up. Because of this, guys, the code changed in 2000 and some, I think 2005, and they said if you have multi-wire branch circuit, we want you to tie both of them at the same time, tie them together. The reason for this, because if you're doing maintenance on this side and you want to turn, you're supposed to turn the circuit breaker off. You can turn both of them off, and you are guaranteed that all the power is killed in every aspect of this circuit. Any question, guys, about this? Any question? So that's what I want to highlight from the parallel series circuit. It might seem very simple, but I picked the most important applicable to you guys, and I thought to emphasize it. Any question, guys? Any questions? Okay. Go over this as much as I can. So this chapter talks about the AC circuits. Hey, bud. The AC circuits. Everybody knows, guys, how electricity was invented first. We started with DC, right? And we thought DC is the best thing ever God created for the human being. And we powered Edison, powered a bunch of things and motors. We started creating motors, DC equipments, and all this stuff. The disadvantage of DC was you cannot shoot the voltage from here to California. So that was the disadvantage until Mr. Tesla came and he said, yeah, I have a system, the same thing, electrical system, that can actually not only power and run equipment, but also it's easy to transform it from one level to another so you can shoot it across the country. That's really what the AC is. So everything add up, the system came up as a DC, as you can see, guys, a positive, negative, and going all the way, depending on how you do, from the positive all the way to the negative. And if I have, the idea is, if you have, if this takes 100 watt, and I have 100 watt worth of power here, the current will go from here all the way, burn itself in the light, and come back. Come back is a reference, guys. It doesn't come back. The power usually goes from the source directly into the sink, source to sink. So here's my question for you. Here's my question for you. If you guys have a 15 horsepower motor, if you have a 15 horsepower motor, okay, everybody's with me? No, let's just say 3 horsepower motor. You have a 3 horsepower motor. Can you guys hear me? If it's a DC 120 volt, or AC 120 volt, or AC 3-phase 208, how much power, which one will consume more power? If I have a 15, not 15, let's just say a 3 to make it applicable. At 3 horsepower that can run at 120 volt DC, or 120 volt AC, or runs at 208 volt AC, this is 3-phase, or run at 480 volt AC, 3-phase. Which one will consume more power if you run these voltages on which and the same horsepower to run it at these voltages? Granted, we have to design it to be run. You can't just have one motor guys that run at all these voltages. You have to design it at 3 horsepower. Which one do you think is going to consume more power based on which system? Same. Did you guys get that one? The same. The amount of power, 3 horsepower. So I can suck 3 horsepower out of the system at 120, or I can DC or AC, or 3-phase 208, or 3-phase 480. This is the single most important thing. If you get this in your brain, the power is a power. Like you going from here to your house, you can, I told you guys that before, you can drive your car, the outcome is the same, you went home, you can ride a bike, a donkey, a horse, airplane, but the outcome is what? The same, you went home. And that's the same thing. I have a motor, 3 horsepower motor. I can burn that baby and run it at 120. Granted, it's designed for 120, or for AC or DC or 3-phase. The key point, guys, is a power. So, but you have to design it for it. The voltage changes. So what changes when you change the voltage? Anyone can tell me what happens when you change the voltage? Big I change. What's I? The current. The higher the voltage for the same amount of power, the lower the current. So which one, in this case, what do you expect the current to be the lowest at which point? Right here, the highest voltage will give you the lowest current. Who cares? Now, lowest current means smaller conductor, more efficient. Smaller conduit, more efficient. Less voltage drop, more efficient. Can you guys see? Efficiency. It's coming into the efficiency. So that's really the difference. Why did we go from DC into AC? One reason. AC is more efficient to transmit and distribute than DC. Why did we go, when they went from DC guys to AC single phase first? Okay, they found it's really superior to the DC. Great, now let's go back and try to get 2 phases. They created a 2-phase system, and they said, okay, it's better than single phase. Now let's experiment with 3-phase system. So they start experimenting with 3-phase system. They found it's more superior to the 2-phase system. And then actually they start adding 4-phase system and 5-phase system. And the industry decided that the most efficient system that you can create internationally is a 3-phase system. You start adding more phases, adding more coils, basically. It doesn't give you a whole lot. It doesn't make the system more efficient. And that's how the whole world almost standardized in a 3-phase system. Different voltages, 3-phase system. Any question guys about that? The outcome is the same. At 3 horsepower, you can burn it at any of these voltages and you still get the same outcome. The fan is running. Any question about that? That's really the major concept. Now in a DC, the current and all the stuff, as far as we're concerned, the current goes one way in DC. In AC, the current is alternate, so it goes this way and back, forth. I don't care about the current. What I care about is the power. Where does the power go? One direction, from the source into the load. That's it. The current goes and comes back. I care less about the current. I care about the power. The power goes always in one direction. And all these voltages, from me, the source, into you, the sinks, or the loads. That's it. In any of these voltage and DC or AC. Any question guys about that? Any questions? So that's the concept that I hope that I would drive through you, or make sure that you understand it fully. Direct current, we got into the DC. Right now with this day and age, guys, the funny thing is we're going back a cycle to the DC now with solar system generated at DC. So the concept was in the world, guys, at one time is if we generate in one location, burn all this coal and make it so disgusting and burn whatever, and then transmit it across the country to the major cities, that's a great idea. And it lived for years. That's what we did power. Now the concept is slightly changing where if we can distribute the generation and put a generation right next to every load. An example of this is a solar system, the wind system. You can put a solar system, that's a generator, micro generators right on the roof, generate power and consume it locally. If you can, if you can't, you don't have enough room, shoot it across the grid to your neighbor. So that's the whole concept of DC is coming back, as I said. So now the main source of DC that we get for DC motors, guys, is AC. So what they do, they have a bridge like this. So if I have a DC motor, 30 horsepower, 240 DC motor, that's the only way I can get a DC to power this motor, my DC motor, is by taking an AC, because that's that we standardize on an AC system to transmit, distribute, and convert it into DC. You have to rectify it slightly and then dump it across your load, which is happy to be the 15 horsepower motor or 30 horsepower motor. Full rectification. If you guys, DC motor is still, the advantage of these DC motors, guys, they're still more robust. Speed control is great for them. For conveyors and so forth, they use them a lot. And how do you get a DC motor to run a conveyor? No problem. Take an AC circuit, bring a DC drive here, so you can convert it to DC, and at the right voltage, and dump it across the coils of the motor. So that's what you can see, guys, the conversion. And I'm not going to go through the conversion, guys. I've done that. You smooth it a little bit, and you've got yourself a DC. You've got yourself a DC. Anybody knows what the RMS value is? When you say 120, when you say, so this is 120 volt RMS. You guys remember that with Gary? Root mean square value. You heard this root mean square value, RMS, is actually equivalent to a DC value. Equivalent to a 120 volt DC. What they're telling you is because AC fluctuates in voltage, they decided, and the peak is this is different. The RMS is right here, right? The peak is square root of 2 times the 120. They decided because it fluctuates, that particular value is equivalent to actually burning this equipment at a 120 volt DC for all practical calculations. Because the voltage goes from 0 here all the way to, this will be a square root of 2 times 120, the peak, all the way to 0 again, peak, and all the way. So which voltage you're going to use for your calculation? Root mean square value. The effective value, which is equivalent to a DC. Just think of it this way. That's when I say 480, root mean square value, that's equivalent to a 480 DC line. Done. That's all what you need to understand for all practical calculations. How alternating current to produce? You guys know the most important thing is induction. The single most important things, guys, is induction. As we all know, if you have a magnet and you move a wire in the field of magnetic field, you create a current, right? That's induction. Induction. So if you have movement in a magnetic field, you create a current, and vice versa also. So what they do is, back into what we generate right now, is you have a prime mover. They call them prime mover. You have a diesel engine generator, a diesel engine, literally running a coil, running an alternator right through a coils, multiple coils, which has a magnetic field. So as you run these the rotor, guys, through the coils, you're creating, because of the magnetic field induction, you're creating current. You're creating current. And I'm not going to go down to the basics of this, guys. We're going to go to the next level. But that's really the concept of electromagnetism. The concept of electromagnetism. Here's what we're talking about, guys. If you have magnets and you move a coil through it, you create power. When I was in college, Chris, in my college and in engineering college, they call these machines. They call the generators, transformers, and motors, all of them are called machines, electrical machines, for one reason. Because if you put a prime mover, if you burn diesel and you move something, rotate something, you get power from this side. The opposite of true. You bring electrical power from this side and you put a rotor through it, it will make the rotor rotate. Now you create a fan, a motor. See the opposite? This way you got electrical power, convert mechanical power into electrical power. The other way you're converting electrical power into mechanical power. And the transformer, nothing is moving. By induction you create one voltage, the same amount of power at one voltage and current level, induce it into another coil to create the same amount of power at different current and different voltage. So call them electrical machines. So it's really, that's a concept without getting into the and it gets of course more exciting than that with alternators and so forth. And I'm going to go directly into generator. Generators, as you can see guys, you create a prime mover right in here. There's a de-excitation on the rotor, but really what you're creating right here is the prime mover. This is where my rotor is tied to your car's engine. Exactly, an engine. Engine's driving here. You're rotating this baby here. Oops. Where did it go? You're rotating this alternator. You're rotating that, and by putting DC, look what they do. They put a DC right on the alternator. By doing that, guys, you create a magnetic field here, and by creating a magnetic field here and rotating it, you induced voltage into the coil. By inducing voltage, the smarter than Chad, the minute that you induce voltage and you tie that voltage across a load, you create a current. Then you have just created a power source, electrical power source. What's the law? The law of physics, guys, energy will never be dissipated. You can't, what's the word? You can't get rid of energy for good. You only convert energy. So what we did here, and again, here's my alternator, my generator is coming over here. You put your fuel right here. You burn fuel. You burn chemical, you burn fuel, make mechanical movement, mechanical energy, from a chemical energy to mechanical energy into this machine to convert it to electrical energy. Whereas losses in between, but you have to burn something to get something. You can't just get electricity. Doesn't come from nothing. You have to do something to make it happen. The sun, the wind. I can't emphasize the alternative. So when you move it, guys, with rotating magnetic field, with some excitation, you can adjust the generator's voltage and frequency. You got yourself an AC generator, Single phase. You add a couple of phases to it, and you got yourself an AC. Here's your DC with conversion, AC generator. This is your single phase AC, as you can see, and you guys have done that, so I'm not going to do much. The way we decided to generate in the US, guys, we generate in one cycle and sinusoidal, and you can see, you can follow the 90 degrees, the location of the coil. You can follow the location of the coil as it goes relative to the location of the signal, how the signal goes up and down with it. And I'm not going to go with the basics there. I assume now, non-sinusoidal wave, this is what we want. This is the bad news. This is a bad news in any electrical signal, at least from a power point of view. Frequency, 60 hertz. If you put 60 of these in 1 second, what do you get? 60 hertz, right? 60 of that signal that you're looking at, put them in 1 second. That went from 0 degree all the way to 90 to 100 to, that will be, what is it? We are 90 here. What would that be? This is 100, 270. This will be 80, 180, 270, and all the way to 360 here. You do that cycle, that one cycle, put 60 of them in the US or 50 of them elsewhere in the world, 50 hertz, and one, it gets you a cycle. I'm not going to get into why 50, why not 150 degree and so forth. That's the most efficient one, 50 and 60s. Pure resistive load. Okay, if you have a pure resistive load, guys, this is a concept very big for us. If you have a pure resistive load, the circle, I can't emphasize. the voltage and the current start and finish at the same time. That's called in phase, and the power factor is 1. In phase and the power factor is 1. Can you guys see the start? That's a power factor is 1, resistive load. Cool? Now if you have, can you see how it starts and reaches the 0 at the same time? You put a couple of degrees on them. Look at this. Non-resistive load, the voltage phase, 1 phase, if it's a 3-phase, look how when we created, in a 3-phase system, we created the phases with 180 degrees between them. Believe it or not, take this, Phil. If you take the voltage V1 at the V1 at 0 degree plus V2 at 120 degree plus V3, that's 120 plus 120. Huh? 240 or those degrees. If you add them up, and I'm missing something here with I have to review my engineering skills. But if you add them up vectorially, believe it or not, they're going to add up to a 0. That's where the complex numbers adding up vectorially numbers. That's where it comes very handy. So if you look at these signals, look at all these signals. If you add them up, add all these signals up vectorially with an angle, you're going to come up with, granted they're all the same size, you can see, you're going to end up with what? 0. So that's the concept of vectorial addition. Lead lag. Lead and lag, guys. You always go by the voltage. Look at this. Lead and lag. 99% of the time you're going to be lagging. 99% of the time you're going to be lagging. Lead and lag depends on the type of the equipment that you're burning. For example, here's my voltage. Always look at the voltage. If the current leads the voltage, then it's a leading circuit. Always look at the voltage. I'm sorry. If here's the voltage here, the current here is leading the voltage, right? Start before the voltage. The current here is lagging the voltage. Lags. Always look from a voltage point of view. Here's the voltage. Does the current start before the voltage? Leading it? Yeah, leading here. Look at the voltage. Does the current start after the voltage? Lagging? Right? This is a lagging part. Always from a voltage point of view. Because that's the only thing that's constant for us is a voltage, guys. Current fluctuates and changes. Lagging. Can you write down here 95% of the time you're in this situation? Current, no, the lower situation. 99% of the time, 95% of the power, you are in the lagging situation. Capacitor lags. So lagging situation. So the current voltage, no, this one, I want the current lags the voltage. Here's the voltage, the current start, here's the voltage, yeah, right here, 95%, you're right in here, which is the current, always from a current point of view, lags the voltage. The current from a voltage, so the current leads the voltage. The voltage stands at the voltage, the current leads the voltage. So 95%, you're going to be right here. Anybody knows why 90% we're at the lagging power factor? Because most of what most of what we burn is what? Motors. Motors are induction load. And I'm not going to, everybody knows, guys, the impedance. So for induction motors, you have the Z impedance here. It's XL, and this is equal 2 pi times F, the frequency, 2 pi, the frequency times, here we go. So it's a 2 pi FL, right? This is the impedance here. This one is Z, the impedance, equal XC, and equal 1 over 2 pi FC, right? You guys remember that from the days of Ryman? 99% you're going to have an XL. Why? Because most of what we burn is motors. Most of our major loads, air handling units, chillers, boilers, air handling unit, chillers, what else? Fans, exhaust fans. Almost most of them are induction loads. As a matter of fact, we add capacitor. Later on, you're going to see me adding a capacitor to correct the power factor to 100%. You want your power factor, we'll talk about this one, guys, later. You want you want your power factor to be 90% or higher, and lagging power factor. You want a lagging power factor. Lagging power factor, lag, meaning the current lags the voltage, or the current leads the voltage. The voltage lags the current. No, the current is confusing. Sorry. The current lags the voltage. I always look from the right, from left to right. Which come from this side. The first thing you hit is what? The voltage. Voltage leads. So the current, if the voltage leads, what happened to the current? Lags. Remember, Chad gets into his looking from right to left sometimes. But I don't think you have this issue though. Any question guys about this 19%? I promise you we're going to be correcting power factor for commercial buildings and so forth as we go through. Lag and lead, lagging power factor. Always look at it from the voltage. The voltage lags the current, and the voltage leads the current. Always from a voltage point of view. Always. The voltage, based on the voltage, the current lags the voltage, and the current here leads the voltage. Lagging power factor. Instantaneous. We talked about the RMS value, guys. The RMS value. Do you guys remember that RMS value that we were just talking about? This one is basically DC equivalent. So what they did is they took a piece of equipment and they burn it at AC, and then they burn it at DC, and they discover at this value of the peak, you get the same amount of power. So they made it DC RMS value. So that signal is equivalent to our RMS value, a DC value at the RMS, or RMS value is equivalent to a DC value right at the 0.707 of the peak. Peak value, talk about the peak. The only reason, guys, the only time you're going to be using the peak later on, Phil, my friend, is when we do short circuit analysis. We're going to be talking about the peak. So just I want to remind you of that little value later on. It could be affecting how your equipment, circuit breaker, will react to the peak of the circuit later on in short circuit. Other than that, 99% of the time you're using RMS value. Effective value. Okay, with all these guys, calculation and so forth, RMS value. All right, capacitor. Let's go to the capacitors. A few things about capacitors, guys, to remember from a power point of view. Capacitors always make a leading power factor, so the current will lead the voltage. So, couple of applications for capacitors. In the power industry, guys, two applications for capacitors. One is to correct the power factor. We're going to be studying this later on, to correct the power factor. Another one is to when you convert from AC to DC, so you take it and smooth the AC, make the AC more smoother, closer to an actual, the DC smoother, filter. But really, for the most part, charge capacitors, and I'm going to talk about that one. DC, electrical field. I'm going to go directly into the electric. Okay. Discharge capacitors. A couple of, there you go, determining capacitance. That's what I'm going to do. Weight and so forth. I'm going to go to the impedance of the capacitor. That's what I want to concentrate on. You guys are not going to be building capacitors, surface area and insulation and so forth. The electric, you can increase it. No arcing on the switch. A couple of uses they use capacitor. All this phase relationship. There you go. Phase. This is what I want to emphasize, guys. For the capacitor, as an impedance, as we said, it's going to be Z, and when you calculate it, it's going to be 2 pi F and C. That's how you calculate the impedance of the capacitor. Impedance of a capacitor. Capacitor always make the current. What does the current would do to the voltage? Lead the voltage. Always. Capacitors make the current lead the voltage. Now, Jackson, my friend, some of you will say, which one is better, leading or lagging? Is lagging 80% better than leading 80%? Anybody knows what happens if you lead, if the current leads the voltage? If the current leads the voltage by 80%, you know what happens to the voltage here? You plug in here, instead of getting 120, you get 150. Bad news. You burn equipment. What happens if you have a lagging power factor? A lagging power factor, if you plug in here, and instead of getting 120, you're going to get, see, 100. Also bad news, right? So your leading will make the voltage higher, which is bad news, as bad. Lagging will also make the voltage lower, bad news. So you're going to find this optimum design. You want your system to operate between 90, for the most part, 90%, close to 96%. That's where you want to be. Lagging. That's perfect for us. If you can maintain your system between 90 and 96%, that's okay. That's perfect. You don't want to lead. Leading is not a good idea.
Please explain that. Is that wave not a timeline from left to right?
Yeah, it's when they're here, when they're both of them start at the same time, that's 100%. No leading, no lagging.
All right, but you have to go all the way. If plugging it in starts at the far left of the diagram.
Let's start right here, the far left. So let's say this is 90% leading. Then come over here. Now we are 95%. Come closer. Leading. We're still leading. Coming from this way, I'm looking at this point. Moving this point this way, I'm 90%. Come closer, 95, 96, 97, 98, 99, 100 when we are at the 2 points are matching. Cool? Coming from this way. Now we're going to move back.
Keep going back in time.
So as I said, going this way, you're going to, this point is 100%. So going away from it will be lagging. So that will be 100, 95, 90, 90, 80, and all these points. And you keep going. This way, the same thing. You're going to have 90, it's like the negative, 95, 90, and so forth. Does that make sense? So I always, here's my line. If you're going to, just this line here. So this is my 100%. It's equivalent like to the 0. If you go here, 95, 90, 80. If you go here, 90, this will, okay, 95, 90, 80. All these are percentages. This is lagging. This is leading. It's exactly, guys, like 1, 2, 3, minus 1, minus 2, minus 3. The line number. Think of it this way. And I'm going to stop right here. I'm not going to go look at the time. But does that make sense? Think of it this way. So I can have a 95% leading. So that's also not a good news. So you want to be right. You want to be right in here. Or as close. Your goal for your equipment to work is that's the optimum design. Where's my 95? Probably that's your optimum design. That's the best way you'll be in this area. That's where you want equipment to be in this area. 90 to even not to 100. That's the optimum design for you when your equipment are working. You definitely don't want to be here. or lower than that. Lower than that you can be, but you have to correct. Higher than that you can be, but you have to correct. Believe it or not, I hate to go there. Utilities, transmission lines, sometimes they found themselves with 95% leading power factor. You know what they do? In order to correct the leading power factor, they install reactors, in the coils. They put coils in their system so they can increase the reactance. So you want to be, the optimum design is right in this area. Good point though. Phase relationship, XC. The only thing I want you guys to remember is that XC. How to calculate the XC? We calculated that one. Pi. Frequency. C is the inductance in farads, and you've done a few of these. And I'm going to stop right here. We'll do the inductance another time. Any question, guys? Any question? I know if I was teaching you guys this as a basic, I'll go over it more. I just want to brush your idea. Thank you, Chris. The idea of leading and lagging, I will touch that one later on when we go into correcting power factor, the optimum design. But when we go, guys, correct power factor, and I say the impedance of a capacitor, I want everyone to understand what impedance of a capacitor is. When I say the impedance of an inductor, I want everybody to understand how to do that, right? Because later on we start correcting power factor, adding capacitors. Why do we add capacitors? Because we are increasing the XC to reduce the XL. Okay, so that's why this is building up to the voltage drop correction later on. Okay, thank you.